Welcome back to part 3 of section 5.5. At the end of part 2, we left you with the A matrix and have you finding the reduced row echelon form of him, and the assignment to find a basis for each of the row space, column space, and null space of this new B matrix to make a point here. So if we take our new row vectors, 1, 0, 1, or sorry, 1, 0, negative 1, 0, 1, 2, and 0, 0, 0, we can clearly see that the third vector is a scalar multiple of the first two, and that the first two are linearly independent. So a basis for what the rows vectors can cover from matrix B is spanned by the first two row vectors, 1, 0, negative 1, and 0, 1, 2. Similarly, when we look at the columns of matrix B, 1, 0, 0, 0, 1, 0, and negative 1, 2, 0, we can see that the third column vector is clearly a scalar multiple of the first plus another scalar multiple of the second, namely negative 1 of the first column plus 2 of the second column. So that means that C3 is linearly dependent, but C1 and C2 are linearly independent. So a basis for the column space of matrix B would be the vectors 1, 0, 0, and 0, 1, 0. And finally, the null space of B is what B sends to the null vector or the 0 vector. And if we check out this system here, well, we've already played with him. He's already in reduced row echelon form. So the null space would be the vector 1, negative 2, 1. Now, let's take a look at the two bases for the row space. So remember that we have in blue and orange the 1, 3, 5 and 0, 2, 4 vector, and in red and black we have the 1, 0, negative 1 and 0, 1, 2 vector. And notice that those two pairs of vectors are still in the same plane. So actually the 1, 3, 5 vector with the 0, 2, 4 vector is a basis for the same space, the same plane as the vector 1, 0, negative 1 and 0, 1, 2. So these two vectors. So these two pairs are bases, different bases, but for the same space. So the image, or the computer made us think that the bases for the row space of A and the row space of B are the same. How can we tell if two different sets of vectors are two different bases for the same space? Well, we check to see if each element in one basis can be expressed as a linear combination of the other set and vice versa. So let's see how this works with our vectors from the row space of A and the row space of B. Let's write those guys down. For row space of A, our vectors were 1, 3, 5, and 0, 2, 4. Okay. And for row space of B, let me do this in blue. Our vectors were 1, 0, negative 1, and 0, 1, 2. Well, we can clearly see that the second row vector in B is a scalar multiple of the second row vector in A. But let's go ahead and check and see if we can't express the vector 1, 3, 5 as a linear combination of the row space vectors in B. So we want to see if there's some k1 times 1, 0, negative 1 plus some k2 times the vector 0, 1, 2 that will make the vector 1, 3, 5. That's going to set up for us a matrix and let's see if we can't figure this guy out pretty fast. Well, if we rref, we should get this matrix, meaning that to make the 1, 3, 5 vector, I'd use one of these plus 3 of those. Let's check it out. 1 plus 0 is 1. 0 plus 3 is 3, and negative 5 plus 6, I'm sorry, negative 1 plus 6 is positive 5. So we did that. In fact, you can show that each one of these vectors can be expressed as a linear combination of those guys and vice versa. And if you can do that between the two pairs of vectors, the two pairs of sets of vectors, then those two bases cover exactly the same space. So we know that these two are bases, two different bases for the same space. Okay. What about for the column space of matrix A and matrix B? Well, let's remember. So the column space of matrix A was, I'll use them just column matrices. So we had 1, 0, 2, and 3, 2, 1, where for the column space of B, on the other hand, we had 1, 0, 0, and 0, 1, 0. Okay. And you can quickly look and see in the column space of A, they have non-zero Z components, where column space of B, you could never make the Z be anything other than 0. So the column space of A basis and the column space of B basis are not the same space. That's interesting. And finally, let's look at the null space of matrix A. Well, the null space of matrix A was the vector 1, negative 2, 1. And the null space of matrix B, what the B matrix sent to 0 was 1, negative 2, 1. And you can see that those are identical, so they have to be the same space. So these are bases for the same space. Now this brings up something very important. How was B related to matrix A? Well, B was the reduced row echelon form of matrix A. And if we use row operations, the net result is the row spaces will cover the same thing. The null spaces will be the same, but since we're using row operations, the column spaces can change. So row operations will not change the row space. It might make it look like a different basis, but it will still cover exactly the same stuff with one set or the other set. It will still cover the same null space. So the null space doesn't change under row operations, but the column space can and often does. And I'm going to pause right there.